Hello everyone.
Yes.
Thank you so much for giving your time to listen my PhD defense presentation. My name is Arvind Kumar, and my dissertation topic is a feasible solution of the local dynamic map based on binary region diagrams and spatial behavior granularity. So the contents are organized in 5 chapters. So first, I will discuss about the introduction, in which we will lay out the background of our topic. Then we will go to literature review. Then what target problem and what target problem we are solving and what proposal we have given. In chapter 2, we will discuss the core technology, about what core technology we are using in our thesis. And in chapter 3, we will discuss about the methodology and what results we got. Finally, we will discuss, and at last we will conclude the presentation, and we will give the future work, what can be done in line with this thesis. So the number of autonomous vehicles are increasing on road. So in around 2019, there were 31 million autonomous vehicles of some features, which is expected to increase till 54 million by 2024. But before introducing them into the society, we must ensure its safety. So normally now autonomous vehicles use sensors for the safe navigation, but they have limitations. And this is the major concern. So like suppose there is a lidar, and lidar image in dry conditions are like this, and in rain conditions are like this. So in dry conditions, you can observe there are some points which is observed by the lidar, and in rain conditions, there are some points which is not observed by the lidar. So similarly, camera has also limitations, like water droplets can obscure the vision of the camera. So due to this limitation, cooperative ITS can help autonomous vehicles in such critical situations. So to overcome sensor limitation, we can use CITS along with sensor-based navigation. So in cooperative ITS, CITS, we have different ITS station like personal ITS station, vehicle ITS station, roadside ITS station, and central ITS station. So vehicle ITS station is basically with the vehicle, personal ITS station is with the person, and roadside ITS station is mainly used to communicate for a small area, and central ITS may cover the large area. And any ITS station can communicate with any other ITS station. So in ITS station, local dynamic map is the critical component. So local dynamic map has 4 layers. First is static layer, second is relatively static layer, third is relatively dynamic layer, and fourth is dynamic layer, in which static layer contains mainly the static information of a traffic scenario like road information, and relatively static layer contains a relatively static information like position of trees, signals, and relatively dynamic, which is the layer 3. It contains dynamic information which doesn't change very fast, like traffic signal information, weather information. And finally, the layer 4, it contains the dynamic information, which changes at very high speed. So like suppose vehicle 1 moves, and it can update its information in the local dynamic map, like vehicle 2 can also update, and like vehicle 3. So like this, many vehicles can store their location or their trajectory information in the local dynamic map. And suppose vehicle 4 want to use it for the navigation, it can query it and use it for the safe navigation, and it can go ahead. So mainly local dynamic map has 4 layers. So first and second are mainly static, related to static information, and third and fourth are basically related to dynamic information. So now we will see the literature review. So local dynamic map was first introduced in 2010. So it was into safe spot project. They introduced it as a 4-layer model. So later on, LDM requirements based on the ITS station, it can be very different, and it was proposed by Netten et al. And so LDM concept was available, but their performance was not available, and the real implementation. So Simada et al. Introduced it, and they published the performance results. And based on Simada et al. Implementation was based on relational databases. So based on graph database, Eggert et al. Published their results. So also the standardization efforts has been done by the HC and ISO. And using the streaming database and ontology, local dynamic map has been implemented by ITER et al. And in local dynamic map, the standard JSON format was proposed in 2022 by Garcia et al. So in the above implementation, there has been one limitation. There was enough work in how to implement the local dynamic map, but very less emphasis has been given to the data itself. So in our work, we have adopted the information processing approach to improve the safety aspect of the traffic participants. So we are processing an information and saving a data in a form so that it can facilitate the safety of the traffic participants. So first, now we will discuss what target problem we are handling and what proposal we proposed. So first target problem which we are discussing in our thesis is near miss detection. Suppose vehicle are moving and they come to very close, and so they must be able to detect it very fast. So which are the vehicles which are very near to them. So vehicles can update their information in the local dynamic map as their latitude, longitude, or their geohash, or their shared boundary region diagram. So we propose using geohash comparison and also the shared boundary region diagram. Using this, we can in a fast way we can guess which are the vehicles which are near to a given vehicle. So second problem which we are handling is second problem which we are handling is the vehicle's future occupancy. So when vehicles are very near, but their future occupancy also matters a lot. So suppose here vehicles are near, but they are going far in future. But here vehicles are far, but they can come to very near and in the future. So we also want to know the future occupancy of a vehicle. So we have proposed the four things to use the COM circle, to use the geohash and reduced order boundary region diagram, and also the JSON format. So now we will discuss the core technology which we are using. So first we are using a geohash. So geohash divides the Earth space region into several sections. So it also follows a multi-granularity. Suppose we are divided the region into various parts. So if we focus in any region, it is further divided into further more regions. And if we focus on any other part, which is further divided into more smaller regions. So every geohash has 0 to 9 digits or English alphabets except A, I, L, and O. So when we increase the geohash length, so we can detect the smaller and smaller region on the Earth. Similarly, the smaller the geohash length, it represents a bigger area. So suppose we take a geohash of length of 10, size 10. So it will have a distance from east to west as 0.9 meter. And suppose we take, so in 10 length, it is a distance of 0.6 meter around from north to south. So every digits from 0 to 9 and also the characters has a associated binary digits in it. So suppose we take a geohash and we concatenate the binary representation of the geohash. So it creates a unique binary string. So in which if we place this, if we compare the y and yx kind of this alternating bits of the binary string, here y will represent the longitude bits and x will represent the latitude bits. So second core technology which we are using is the binary region diagram. So binary region diagram is basically based on based on Boolean variable to represent it in compact form. Suppose x is a Boolean variable, it can have a value of 0 and 1. Boolean function are the function which takes the input as the Boolean variable and can have output as a Boolean 0 or 1. So we can represent the Boolean function using the truth table. So truth table representation can have a very large number of rows here, and it can go to very large size. Suppose we have a 10 Boolean variable, it can have a size of 1024, and suppose we have a 20 Boolean variables, it can go further large, and so on. And if we go to the 50 Boolean variable, this size will be very huge. So suppose we take a geohash of 10 length, then the number of rows in the truth table will be huge. It is very exponential size. So one alternative representation can be, we can represent it using the binary region tree. Binary region tree are the representation of the corresponding to the truth table. Like suppose here it's 0, 0, 0. So 0 on 0, 0, 0, it will go to 1. And like here it is 1, 0, 0, 0. So on 1, 0, 0, it will go to 0. But binary region tree can also suffer with exponential number of nodes. Its leaves can have 2 to the power k nodes, and also the internal nodes can have 2 to the power k minus 1 nodes. So tree representation can also have exponential number of nodes. So what we do, we reduce the tree representation. So to do the reduction, first we fix the order. So here, like when we are going in this path, we are going from x1 to x3 to x2, and when we are going here, we are going for 1 to 2, then 2 to 3. So this path is not correct. And so like in this tree, it is correct. Like it goes from 1 to 2, 2 to 3. And here in all other path, it goes from 1 to 2 and 2 to 3. So first we fix the order, then we merge the leaf nodes. So every 0 are merged into 1, 0, and every 1 are merged into 1, 1. So now we are able to reduce the number of nodes in the leaves. But still we have a lot of nodes in the as internal nodes. So in internal nodes, we will reduce the nodes whose low and high are going to the same node. So like here, this x3 is this edge and this edge, both are going to this 0, means the presence of the x3 doesn't matter. So we remove this. And also we apply a rule 3. Rule 3, we will merge the isomorphic subgraphs. Isomorphic subgraphs are the nodes which have like here x3, its 0 goes to 0 and its 1 goes to 1. And like this x3, this dotted edge represent the 0 and this dark edge represent the 1 edge. So this x3 as well, on 0 it goes to 0 and 1 it goes to 1. So these two nodes are almost same. So we merge them. So we obtain a reduced order binary region diagram. So now the number of nodes was reduced. So we can see the binary region diagram, also the binary tree as a set representation. Suppose we have a binary string 000, 0110, 0111, 111, we can represent it using a tree. In a tree, it goes from 000 to 1, and whatever string we have, for those strings in these trees will have a 1 value. Like 0110, so 0110 we will have 1 value. Similarly, this is the binary region diagram for the corresponding tree, and it will represent the same set, but it will have the lesser number of nodes. So like here 000, 000, it will go to 1, and similarly for all other binary strings. And also binary region diagrams follows an algebra. So if we take the two binary region diagram and take the OR between them, it represents a set union. If we take the two binary region diagram and take the AND between them, it represents a set intersection. And similarly, the XOR will represent the set symmetric difference. And like here, if this is a BDD with 0110 and 0101, OR operation will give the BDD or binary region diagram, which is the union of these two sets. Similarly, AND will give the intersection of these two sets, and XOR will give the symmetric difference of these two sets. So another core technology which we are using is calm circle. Calm circle mainly depends upon how much car can insert a force on the road, and depending upon how much far it can go. So we determine the maximum acceleration of a car using calm circle. So car can have a longitudinal acceleration as well as lateral acceleration. So combining this force, this creates a circle around it. So when we are going with high longitudinal force, it will have a less lateral force. And when we are going with more lateral force, it will have longitudinal force, less longitudinal force. So suppose these are the forces acting. So equating these equations, we get a maximum acceleration. So in most of the paper, we use for car as a 10 meter per second square, and for truck as 5 meter per second square around. So in our experiments, we have used the maximum acceleration for a car as 10 meter per second square. And also to represent the map to represent a map, it's very important for autonomous vehicles to we should have a highly detailed map. So for autonomous vehicles, so we are using the lanenet based maps. So in lanenet based maps, it has a left boundary and a right boundary, and this combined into a one lanenet, and this represents one lanenet. In one lanenet, the rules inside this are the same, and so in this way we can combine the all lanenets and we can build a complex map for autonomous driving. Like suppose here we have an intersection scenario. Using lanenets, we can build a very complex maps for this intersection scenario. Now we will discuss the methodology and what results we get. So first, like geohash, we discussed, depending upon the size, it represents the size of the region on Earth. So suppose we are taking 7 labels or 7 characters of geohash, it represents a bigger area, and so on. If we go for 8 labels, it represents further smaller region, and 9 labels, it represents an area which has a diagonal of around 6.1 meter. So we divide the space on Earth using the geohash. And since every geohash is a Boolean string, we create a shared binary region diagram for this Boolean string. And so shared binary region diagrams are the binary region diagrams. Like here, this is binary region diagram for one Boolean function. This is binary region diagram for another Boolean function, like so on. So in shared binary region diagram, if we combine this binary region diagram, so if they are sharing any Boolean function, they will share the node here. So like x1 is here, x1 is shared in every binary region diagram. So they will all share a node of x1 here. So suppose two vehicles are in the same geohash. We store the shared binary region diagram for those vehicles. And so if they are on the same geohash, so their shared binary region diagram memory address will be same. So so checking the problem that whether the two vehicles are on same geohash, it gets converted into checking their memory addresses, and this decreases the time of this comparison of these equivalent functions. So this represents a set. So basically this represents a set WYHB3KD, WYHB3KD. So this doesn't preserve the order. Actually, this represents the set. So it can be in any order. So when they match, we check it one by one. So we utilize this shared node to check the equivalence between the two Boolean functions and to find whether they are in same geohash. So in a Ross-based experiment, these vehicles are exchanging in between the latitude, longitude, geohash, and the shared binary region diagrams are created in a server. So we compare. So if we find the distance between the two vehicles using the floating point, so it is around here. And with just geohash, if we compare, its time is around constant around this blue line. And if we compare the shared binary region diagrams, it decreases much. And also if we increase the number of vehicles, the comparison time, the increase in the time is less if we use our proposed approach. So with this proposed approach, we received, we were able to gain the minimum computation time. So then we attempt to represent the behavioral information of the vehicles in the local dynamic map. So vehicle can move to anywhere. It can go like this vehicle can go into the left, to the straight, to the right. So vehicle can have multiple future behavior. For the safety aspect, we want to insert the information in the local dynamic map. Their future occupancy of the vehicle. So we have considered the worst case occupancy of a vehicle. So in worst situation where this vehicle can reach. So this we wanted to insert in the local dynamic map. So we use this calm circle technique to find the future behavior of inverse situation where a vehicle can reach. So this calm circle is basically an abstraction of the reachability analysis. So this reachability analysis is mainly based on reach set. So suppose we have an initial state of, and this red box represents the initial state, and we are only allowed to go east, west, north, and south. So the reach set on the time 1 will all these blue states, and similarly at time 2, if we attempt, the reach set will be all these blue states which we can reach. And similarly in time 3, these are the blue boxes which we can reach at time t equal to 3 if we follow our directions only if we go east, west, north, or south in every time step. So reachable set is the union of all these reach sets. So at time t equal to 3, if we want to find the reachable set, we take the union of all the reach sets before this time t equal to 3. So these are the reachable set at time t equal to 3. Then model of a car. So the model of a car which we are using is a point mass model, and this is the state space representation of a point mass model. Though point mass model neglect a minimum turning radius of the vehicle, but anyway, we get using this model, we get the over approximation where vehicle can reach. So we can use it for the safety purpose. So any other model will give the subset of this model. So we use the concept of abstraction. So suppose this is our model and this is the reachable locations of the vehicle. So we say the abstraction M1 is the abstraction of M if it includes all the space reachable by a model M. Similarly, M2 is an abstraction of M1 and Mi is the abstraction of M2, M1 and M, and so on. So for the abstraction, we use the concept of calm circle. So calm circle basically projects where a vehicle can reach in the future. So these are the locations where vehicle can reach if it is traveling around this axis with a velocity v. So at time tk, or this circle is around time tk and this circle is at tk plus 1. So its center will be at v tk plus 1 and the radius of this circle will be half a max tk plus 1 square. So this is the area if vehicle is traveling with this speed. So it will be around this region, and if and this region radius, this region creates a circle and its radius is half mx t square. So then we created a modified midpoint generation algorithm. So this is a midpoint generation algorithm. So to find all the geohash inside a calm circle, we first we generate all the geohash inside a calm circle. So suppose this is one circle, this is generated in a midpoint generation algorithm. So every circle has symmetries. If we can generate all the points in the first octant, we can also generate the points in the other octant. They have a symmetry. Like here in the green, we are generating here like this. And similarly, yellow will grow, orange will grow like this. So we modified this algorithm and created our own to find all the geohash. So in this algorithm, we generated all the geohash first in the first octant. And based on this octant, we find this all limits. And based on this, we generate all the geohash till this limit, and kind of. And we find all the geohash inside a calm circle. So if we have a if we have a circle, we convert it using the we convert it into a binary region diagram, and further from binary region diagram we convert it into a JSON format, and from JSON format we can recreate a binary region diagram. So binary region diagram follow an algebra. So suppose we have two circle and we have a binary region diagram for it. And suppose we have another circle, we have a binary region diagram for it, like here. If we take the intersection of this, so intersection of two BDDs gives the common and common element in the set what they have. So we can get the common area here. And if we take the OR operation, we will get the union of these two regions. So in our experiment, first we are considering a scenario 1. So we created this map in JOSM, and then we loaded this in a ROS-based environment. So this is the region around the vehicle, which is union of the calm circle at 0.3, 0.7, and 1.2 seconds. And this is the region around the vehicle, which is the union of the calm circle, which is at 0.4, 0.8, and 1.2 seconds. This is the output of the simulator. So this is a projected area for any particular vehicle, and the speed is chosen. It is in between the 4 meter per second to 12 meter per second. So this is scenario 2, which we are taking for a city scenario. We created this map again in the JOSM environment, and based on this, we are generating the data for 50 vehicles, and we are storing the vehicle ID, vehicle type. So vehicle are all our vehicle, our vehicle are car here, and its velocity in the X and Y direction. Then the vehicle's latitude, longitude, its linear ID, and the VDD we are storing in our local dynamic map. So this is the local dynamic map we created, and this is based on the Simada et al. Paper. So we have our information storing tables for layer 1, and also we have tables for the layer 4. And also we have a long road element. So this links the tables in the layer 4 and layer 1. So ego motor generates enter data in ego motor vehicle table. So, and also the motor vehicle table is used to insert the information of other than ego vehicle, insert information in this table. So vehicle updates its information in layer 4, and using the along road road element table, which is the linkage between this layer, we can query the layer 1 tables as well. So based on the data, we insert 50 vehicles. In every 50 milliseconds, we insert the data in the local dynamic map. And in 100 millisecond, every 100 millisecond, we execute the query to find where our vehicle is situated now, and also what are the vehicles which are surrounding our vehicle. And then we find the collision detection time, means avoidance time, how much time it took. So this is the chart. So if we are also inserting a BDD, and if we are not inserting a BDD, is represented by red. So we observe that if we are inserting a BDD, little jump in time we see. This is because now we are not inserting only a local point-based information in the local dynamic map. We are also inserting much more information than before. So, but we believe that our approach can help in the following applications which are mentioned in this standard, HC standard. So it can help in the across traffic turn collision risk warning, or merging traffic turn collision risk warning, cooperative merging assistance, or intersection collision, and also in cooperative forward collision warning. So following is the chart for if we are considering BDD based collision avoidance task. So we say that around 40 vehicles it was working in real time, which is much below than 100 milliseconds. And also when we don't consider a BDD. So then we discuss what are the problems with using this approach. So there can be multiple problems. So which there are limitations on the BDD. So the limitations are the BDD are mainly dependent on they are highly dependent on the order of this variable, means in what order we create a BDD. So suppose we create a BDD for this kind of function. In this variable order, it has less number of nodes, and if we create a different order, it has a different number of nodes. So for our case, for the geohash, we took the linear order from x1, x2, x3, x4, and so on. We go up to x50. So because this has the minimum number of nodes, BDD creation will take for a geohash. And also one more thing we must take care if we used our approach, when vehicle exchange information in between them. So there every BDD should have a unique ID for their nodes. So whatever participating vehicles are there, they should have a unique ID, because the BDD based algorithms, they use this ID uniqueness for the algorithm processing. And in shared binary region diagram approach, we query the central server. So it is, we don't download the data. So because it is based on memory address, so whenever we want data, we query the central server. So in conclusion, so we will see what novelty we have achieved. So we have successfully modeled the geographic information in the binary region diagram. We presented a novel data representation in the local dynamic map. And so we were able to represent the geographical future occupancy information and using a BDD. And we showed that sharing BDD-based geographical information support algebraic operation between the exchange BDDs. And this kind of exchanging the information between the vehicles, this supports the nature in CITS, how CITS share the data in between them. So these are the tasks we have achieved. So we reported a near miss detection time for floating based calculation and geohash comparison, and also in case of shared binary region diagram. We also reported the data insertion and collision avoidance check time of the linked list based BDD on PostgreSQL database based local dynamic map. So in future, so currently we are considering a 1.2 seconds future occupancy. So in future it can be improved if we take it to the minimum swearing time. Minimum swearing time is the time which is needed to avoid a collision. Or we can use a different kind of database. We can also use a graph database based implementation of the local dynamic map, or ITE based implementation of binary region diagram can also be very helpful, because they have much more speed than the linked list based implementation. And also there are many variants of BDDs like ZDD and MTBDD. So they support some many different algebras like some BDD do, and we can use it for future much more richer algebra. And also now we are sharing the worst case occupancy, or in the local dynamic map, we can share occupancy depending upon the intention of the vehicle. So these are the papers supporting the thesis. So at last, we also like to acknowledge the GSPS and NATO.
Thank you very much. So now let's open questions and comments from the audience. Please turn on your microphone to start your question. Any questions or comments?いかがでしょうか、質問。何でもいいと思うので。
日本語で質問した場合は、英語でトランスレートしますので、遠慮なく質問してください。The Japanese questions can be translated to English, and then any of the person do not hesitate to ask anything. especially for the external member, please send some comment or some question. Thank you very much for your cooperation. Okay, Manu, please.
Yes, thank you, Professor. Thank you, Arvind, for your presentation. And I want to ask one question. In slide number 25, you have mentioned that if the BDDs are same, they share the same memory location. So how that is achieved? Can you explain a little more? Slide 25.
Thank you so much for your question. So your question is, suppose two vehicles share the same geohash. So when we are creating a shared binary region diagram, how they share a common memory address. So this is so we have a pointer. So we have a this implementation is done in a C-based language. So we are accessing is using a Python. So we have an address of this location. So whenever we are creating a shared binary region diagram for the same set, so it is assigned to means the same reference is assigned again to the new variable. So this is mainly done. We can do it using our own implementation, but we have used a library, a DD package, region diagram package in Python. So whenever we create a binary region diagram which has the same Boolean function, it is automatically referenced by a same address. So this is the concept of shared binary region diagram in a compact form. So
Thank you, Arvind, sir. Thank you very much.
Thank you. Any other questions or comments? Sure. 質問いかがでしょうか。
So this is Hiroaki Wagasuma. Can I ask more detail? What is the main achievement you are the success? Very simply.
Thank you, Professor, for your question. Professor, in my thesis, the main achievement is so like before, so mainly we are adopting this information processing approach. So basically data saved in the local dynamic map here. So we can save in any form, means it's location information or kind of any form. But the main thing is that whatever information which we are sharing now, it's encoded in some form, mainly in binary region diagram form. And they form some kind of algebraic properties between them. So So now means two information can be combined to create a new information, to get a new information that they will collide in the future or not, kind of. So.
But I understand that the theoretical advancement is the novelty, but you're saying that in the beginning, the application of ITS. I think some of the mission still remains if you're thoroughly try to apply actual CIDS system. What kind of limitation or remaining problem you have?
Yes, Professor, as far as I can understand, your question means, is this has a limitation, means how it can be used in future? Sorry, Professor, can I get the question again?
Your proposal is you tested in your simulation platform, but in actual use in the society, what kind of the mission you have to solve, or some other people try to solve an actual implementation, the real CITS system based on the your solving.
Thank you, Professor, for your question. I understood. So, Professor, suppose if we want to apply this procedure in real life, so there can be one of the challenge can be, so first, we must ensure that in real life, when the vehicles are exchanging the information in between them, so they should create the whatever BDD they are creating should have a unique ID for every node first. Then also in this shared binary decision diagram case, we said that we can't download the information. Every query should be executed in the central server. And one more problem which they can assign, but which should be handled, it is the very high speed. So if the vehicles are very high speed, then we have to sample more calm circle. So,
could you show us the okay? Okay, so you did, please.
And so one approach to overcome it can be that they can use the envelope of this calm circle. So this is so. Otherwise, I think though results are now in simulation, but they can be used in the real life. So this exchange information can be done, but only the uniqueness of the ID of every node is very important in using this binary decision diagram.
So could you, can I ask one more thing? Could you show us the slide you showed some, okay, centralized, that you're showing the picture, the information centralized in the database. Yes. So one doubt is, okay, if high-speed computer are done in everything together in a cloud base, but the people discussing now, cloud computing and edge computing, how is it possible to separate the computation in the server based and the edge based, or binary decision, the FPDD only accept the calculation and the cloud server and connecting everything. Is it possible to separate such an edge or parallel computing for the some computation in the beginning and then integrate them together the two-stage or something else.
Yes, Professor. So your question is means is it can we take our approach to the cloud server or means edge computing, and is it necessary to use a central server? So Professor, it is in case of ROBDD is not compulsory, means if you are using a cloud server or means distributed computing kind of this. But if we are using a shared binary region diagram, then it becomes very important to use a central server. So it has a limitation in the real life. But in case of this case, this doesn't have a limitation until and unless vehicle produces a unique BDD. So we can assign some mechanism to every vehicle to us create a BDD which creates a unique, like every vehicle has a number, so every node ID is preponed with those vehicle numbers. Kind of.
Okay. Okay, one more question. So okay, now you're focusing in the the spatial information only, including the prediction of the movement. But in a sense, if you can collect data or planning an action or some other different type of information, it is possible to implement such a BDD-based calculation for the coordination of the vehicles.
So, Professor, so your question is if BDD can use some kind of action information
Yes.
to coordinate.
Writing turn right, turn left, or yes, stopping or signal information, something.
Yes, professors. So basically, in the local dynamic map setup, we can achieve it, I think. So in local dynamic map setup, suppose we store the geohash of every lane. Suppose in the layer one of the local dynamic map. So in layer one of the local dynamic map, we can store static information. So suppose we store a BDD for all the geohash present in particular lane, and suppose vehicle has a movement here, and it creates some kind of occupancy, future occupancy. So if it has the intention of going left here, suppose from here, so it can take the intersection, whatever it has taken the future occupancy, what projected, and with the BDD intersection, with the intersection of the BDD for this static layer. So if we have a BDD for all the geohash present in the static layer, then we can take the intersection with the projected geohash BDD. So it will give only the BDD for those particular lane.
Okay, thank you very much. 担当先生、なんかラジ君が手を挙げてます。
はい、ラジ、please。ラジさん、どうぞ。
Sorry, thank you for your presentation and nice topic. I have one question about the server, the central server. I think the cars should communicate with the server. How did you consider the communication part in your simulation and the delay in this communication? And the speed of the car, I think, will affect that delay because of hopping, change from cell to cell. Did you consider that in your simulation?
Thank you so much for your question. I understood. So your question is, so when the vehicle update their information in the local dynamic map, so when the vehicle update their information in the local dynamic map, so do we consider is it in real time or not? So in our experiment here, every vehicle here, there are 50 vehicles. They are inserting data in every 50 milliseconds in the local dynamic map, and we are querying in our 100 millisecond. So we have followed this standard. This is the ATSI standard, and according to it, so vehicle for the real-time operation, every message should be able to update within the 50 milliseconds, and every vehicle should be able to query between in between the 100 milliseconds. So for the real-time operation, then it can support it. So we have considered that this scenario for the real-time operation. So based on this, we see that up to 40 vehicles for the database which we are using is Postgres database. It is working on real time. So
Thank you. Is that effect on the speed of the vehicle? I mean, is that limit the speed of the vehicle? Like we cannot like exceed for example, 40 kilometers per hour or 50. Is that make limitation for the speed of the vehicle?
okay,
These
so
standards, I mean, this standard is 50 millisecond or 100 millisecond.
okay, your question is, do we consider the speed of the vehicle and do it interfere with the communication and updation? So speed of the vehicle is not considered because in our experiment, we are considering that there is no communication delay between this. But in real life, it's a very good question. Thank you. But in real life, do there some delay occurs due to the communication and communication setup? So
Okay, so in simulation, you did not put some parameters for delay. You assume there's no delay.
yeah, for our experiment, yeah, this was not considered like. So in real life, this may occur that there can be a packet loss, or there can be a delay in the communication.
Okay.
So maybe in the future this can be handled.
Okay. Thank you. Thank you again for your question.
Yeah, 丸坊君が手を挙げてます。
Thank you, Arvind-san, for the great presentation. Can you go to slide number 49? I didn't quite understand one thing. Can you explain? Here you mentioned that each vehicle interacts with each other, and each vehicle, if I understood correctly, that they calculate their individual COM circle internally inside the vehicle. And for example, in this case, in this slide, vehicle number 1 and number 2, the COM circles intersect with each other. So where the intersection calculation is going, is it on the server or is it on the car itself?
Okay, thank you so much for your question. So your question is how this calculation for this collision detection is done, whether it is done at server level or at the vehicle level.
Yes.
So basically there can be multiple ITS stations. So basically there can be multiple ITS station. So like here, this is personal ITS station, this is vehicle ITS station, this is roadside or central ITS station. And every ITS station can have a local dynamic map in it. So depending upon what kind of ITS station we are considering, we can perform the task. So in our experiment, which we are telling, the result which we are proposing, here we say it is for 40 vehicles, and this is for vehicle based ITS station. So it is sufficient because a given vehicle in nearby region, it's 40 vehicle, it can handle the 40 stations. But it can happen in any kind of ITS station. So means this calculation is not fixed for where it should be done. So if it is this vehicle 1 send information to the vehicle 2, then vehicle 2 has its own ITS station, that is vehicle ITS station, and it can compute the intersection of both the binding region diagram. Or if these two vehicles are updating somewhere else in the central server, so it can done in the central server too. So it is not specific. It can be done everywhere in any ITS station.
Okay. Thank you.
いかがでしょうか? Any other questions? Okay. Okay, thank you very much for the presentation and the questions and the discussions. So it's time to finish the session. So please give a big hand to Arvind for his great presentation.
Congratulations.
At last, I like to thank all the committee members for their valuable comments. Thank you so much for your help. And also to the Bogasuma Sensei for his consistent support throughout the PhD journey. So I'm very thankful.
はい、では終わりにしたい